In this video, we're going to dive deeper into how neural networks and machine learning actually works behind the scenes. And if you're learning machine learning, you've probably come across a diagram that looks like this, which oftentimes, if not most of the time, confuses people because it's a bunch of circles and arrows, and the explanation is usually just as confusing. Well, it's simple. You take your input circles and move them through your circles, and you end up with your voila, neural networks. And so that's not really a very good explanation. At least it wasn't very good for me when I was learning. So hopefully we're going to break this down, make it really simple, because it's not really rocket science going into this. It's not simple like ABCs, but it's not super complex either. So if you watch this video a few times, it'll give you a big head start on what neural networks are. And maybe even you'll be able to go and code some yourself if you have coding experience. So here's the picture of the neural network. We're actually going to use this diagram later, but you're going to understand it. So a good way to start is to block off this center layer. We're going to call that the black box. And this is what we've been doing if you've been watching my last two videos on machine learning. Let's just stick to the input and output data, the training data, right? Given this information, here's the outcome. These are our input dimensions and the outcome dimensions. And then somewhere that black box in between runs over that information over and over and over again. And each time it has 1,000 knobs on that black box, and it twists a little knob just a little bit at a time until, wow, the black box is tuned and we can give it new input information and get the correct predicted outcome. And so this video is going to dive into the hidden layers area, that black box, and how we configure it and what it does. So there's some common configuration options no matter what machine learning or neural network library you're using. There's some common configuration options that you're going to come across for configuring that neural network. One, how many hidden layers do we put in that black box? We know we have an input layer and an output layer. How many layers go in the middle? And usually one is where you need to start off with. That's pretty simple and straightforward. And then how many nodes, how many neurons go in that hidden layer? And there's a few different ways you can kind of give yourself an answer to that. There's not an exact science to it. A good path is if your input and output dimensions are drastically different, go somewhere in between. If you have 7 input values and 2 output values, then maybe 3 or 4. Also, you definitely want it to be less than 2 times the input nodes. If you get bigger than 2 times the input nodes, you can get a situation called overfitting, where you're just not going to get accurate outcome. Also, 2/3 the input nodes plus the output nodes, that's a good kind of way to go. And so if you kind of run the math on these 3 situations, you'll kind of get some ideas on how many nodes that hidden layer should have. An activation function. This is very important, but I'm not going to go into it right now. Also, learning rate and momentum are important, but I'm not going to go into those right now. Lastly, the iterations and the desired error level. So iterations is how many times it goes over all the data in your data set. The desired error level is how accurate do you want this thing to be? And depending on what you're going for, basically training stops until you get to one or the other, till you've gone through, say, 20,000 iterations, or until your error level is 0.0001 and it's pretty accurate. Whatever you set, the training's going to go till you get to one or the other of those. So that's the configuration options. That's actually not too bad. That's how you tune your black box. So if you have a little bit of knowledge as to what the black box is doing, you can usually tune a neural network and move on from there and get good results. So let's go to a real example using these circles and arrows that we have from before. We have a data set. This data set gives us fur color and weight of animals, and also tells us if those animals were who's its or what's its. So we want to go through all of that data, train our neural network to predict who's its and what's its based on fur color and weight. And so we've chosen 3 hidden layers based on the options that we showed you on the last slide. So let's go ahead and then get our neural network initialized. So to start off, we basically want to create a stupid brain, a brain that knows nothing. So we're gonna just randomly create a bunch of weights. You can see, I'm gonna get my mouse out here. You can see we've assigned a 0.1 weight, a 0.3 weight, just completely random numbers. And these neurons, these hidden layer neurons and nodes, are gonna also get a bias. Consider them coming in with an opinion already, even though we don't know anything about how fur color and weight apply to who's its and what's its. We're just gonna start making guesses based on our bias. Consider them the liberals, conservatives, and libertarians, and we're gonna get them all in a room, show them a bunch of real life data, and hopefully at the end of the thing, they'll all agree on what is truth. I'm not gonna say anything. Nope, not going there. Moving on. So that's our hidden layers. We initialize the network with just a bunch of completely random weights and biases. And then moving on from there, we're going to start with the first entry in our data set. So entry number 1, we have an animal, fur color 25 and weight of 15, and it's a who's it. It's a who's it 1, it's a what's it 0. So now we start moving these input dimensions through the neural network. It's called a feed-forward neural network for that reason. So basically what we're going to do is we're going to take both of the input dimensions, we're going to multiply them times the weight, and then add the bias. So here we go. Node 1 gets fur times 0.1 plus weight times 0.8. See, we have our 0.1 weight and our 0.8 weight. And then we're going to add the 0.71 bias. So that's node number 1. So we're basically saying, let's randomly guess how these 2 nodes affect our outcome. Let's just start with a guess. And then we're going to do that for each node. A completely different set of weights and biases here. A completely different set of weights and biases here. You can see when we get down here, we're taking fur times 0.57 plus weight times 1, and we're adding a 0.09 bias. So we're basically making a random set of guesses, and then we do the magic, and then we run all those through an activation function. And here's where the activation function is important. Here's where the magic of neural networks comes in, is because we're trying to figure out answers to nonlinear data. And so I'm going to do a little bit of a tangent over here and kind of show you the difference between linear and nonlinear data. Linear data is a straight line. We can say that, hey, as the weight and the fur color goes up, we know it's a greater chance of being a who's it. As it goes down, it's a greater chance of being a who's it or what's it, or hey, if the fur color's high or if the weight is high, it's always going to be a who's it, right? So you could use this with some species. If it's big, it's a dog. If it's small, it's a mouse. If it's smaller than a certain size, there's no way it's going to be a dog. That's linear information. You don't really need a neural network to solve answers on these. You just need a little bit of math, and the data should be pretty clear as to how the input correlates with the output. Non-linear is like this. It just turns out differently. It may be high here and high here, or it may kind of follow some unusual curves that are really difficult to figure out on your own. And so that's basically where your activation functions come in. We're going to use a sigmoid or a tan or tan-H or a tanch, depending on who you are and where you come from. And so we're going to basically apply that sum value, and we're going to run it through one of these functions and introduce nonlinearity to our neural network to help us kind of find out the answers to those questions. So we've taken the sum, right? We've taken the sum times the weights, and we've added in our bias, and we're going to run that through our activation function. Now we're going to get a non-linear guess here. And then we're going to continue running through until we get to our outcome. And let's just throw out a number here. Let's say we ran it through our activation function, came through again here, and we end up with just a random drawn out of the hat guess that it's 0.3512, that it's a who's it, and 0.781, that it's a what's it. Completely wrong, right? Our neural network is stupid. It came in with just biases and random numbers and made a guess that was way off. So then it's back propagation time. We're going to calculate the error and the delta, which is the difference. And we're going to adjust all the weights and the biases. We're going to go backwards through each step, and we're going to adjust these biases and these weights some. We're not going to necessarily adjust them all the way, but we're going to adjust them some. How do we know how much we're going to adjust them? Well, we do that through our configurations. The first one is learning rate. Learning rate says how much should this step outcome affect our weights and our biases. And learning rate is, you almost want to think of it as personality types. There's the slow calculating type of person where if you were to show them, here's a cat, here's a dog, they're going to say, I have some ideas, show me some more. And then after you show them a whole bunch, they'll slowly lean into the answer and then come up with a very calculated answer. That's a low learning rate. A high learning rate, a ridiculously high learning rate would be, oh, you showed me a cat and a dog. I calculated the differences between the two. I know the difference. And then you show them a really fluffy cat and they think it's a dog because they had way too high of a learning rate. So that's what learning rate is. And then momentum also says, how should our past outcomes affect our weights and biases? So past outcomes could say, last video, I showed you a presentation on how a neural network works and what's going on underneath the hood. So to kind of help illustrate it in a different way, we're going to do a real-life training scenario here, and we're going to actually do a ton of console logging and output to actually help you see what it's doing to the real data that we're training. So I've gone ahead and hacked brain.js and added tons of console logging that should really help us understand what it's doing to our training data. And then if you've been following the examples we've done in the past videos, all of which will be in the description, then you'll really understand this. This is very simple what we're doing. We're creating a neural network and we're training it with one piece of data, and we're only doing one training iteration, which of course is silly in real life because normally we'd have tons of training data and 20,000 or so iterations. But we don't want to do that because that'd be just log bonanza. So we're going to go ahead and train this one piece of data one time, and let's show you what happens. So there we go. I've gone ahead and run it, and let me scroll back through my logs. Yes, this is all a mess. And before I start going through this, I'm going to take the final log output and put it in a gist and add it to the description here, because if you step through this, it actually is really helpful. Doing things like this actually helped me understand how neural networks work when I was learning them. So what we've done is we've started training, and it says, hey, here's our training data. We have basically one piece of data, and it's got an input and an output. So let's go ahead and run input set 0, which is this whole thing right here. We only have one input set. And so then we're going to look at our neural network. Hey, layer 2, which is this layer right here, layer number 2, it has 3 nodes. Layer 3 has 2 nodes. So layer 2 has 3 nodes. Let's start with node 0. So we're going to calculate this node, then calculate this node, then calculate this node. And then we're going to move on to these. Calculate this, calculate this. So let's start with node 0. Hey, look, we've initialized it with a bias. There's our bias. And we've also initialized weights for each of our input values. So 0 has been given a weight, and dimension 1 has been given a weight. So dimension 0, which happens to be 0, has been given this weight and that. So we're going to calculate the node value, which is 0 times this, 1 times this number. We're going to add those two calculations together and then add our bias as well. And we end up with a value for that node. But we're not done yet. Then we're going to run that through the sigmoid function, because our neural network by default with brain will use the sigmoid function. And there we go. That is the value for our node. Node 1 is done. Boom. Let's go start with node 2, which I'm accidentally calling node 1 there. Node 0, node 1. And now node 1, we're going to do the exact same thing. Different biases, different weights, same values, same input values. 0 and 1. Now we're going to go on to node 2, same thing. New bias, new weights, same input values of 0, 1. You can see we have all of our sigmoid output values done. So now let's move on to layer 3. Layer 3 has 2 nodes, 2 output layers for our neural network. So there we go, we have our biases, and look, we have 3 inputs now because we have 3 of those middle hidden layers. Here's those outputs. You can see 0.45, 0.47, and 0.459. For example, node number 3 has 0.459. There's that number. So that's our input to the next layer. And we're going to multiply those by the weights. We're going to sigmoid them. And now our 2 output nodes have a final value. So there's our final value. Let's go ahead and calculate the error, the delta. And then we're going to go ahead and back propagate. And we're going to go make some adjustments to the weights. Here's our weight adjustment formula. It's our learning rate times the delta times the value of the current weight. And we're also going to add the momentum plus the prior change that we made, which is going to be 0 right now because we didn't make a prior change in the last step. So this is basically just doing that for step number 1. This is going to output to 0. So then we're going to go ahead and make an adjusted change, 0.00192. We've modified our weight for this layer. We've modified the weight and we've modified our bias as well. Down here, we've adjusted the bias by that much. So we adjusted our bias, we adjusted our weight. Let's go down to the next layer, and let's go down to the next layer. We've adjusted all of our biases and our weights. We're ready for the next iteration. So let's go change this now. Let's run 2 iterations. And let's look at what happens on iteration number 2. It's going to look exactly the same, except for the weights and the biases are all going to be different. The weights have changed, the biases have changed ever so slightly because our learning rate is 0.03. We don't want to make these brash guesses and say, oh, you showed me one piece of data one time, well now I know exactly what the answer is. If you'll notice now, our momentum times change has changed a little bit. Since we had a prior change value, we actually have a little bit of momentum right now. So the last iteration's change value is going to slightly affect this iteration's change value. Basically, if this number was on its way down, we're going to make sure it wants to go down at least a little bit. And so that's basically how that works. That is 2 iterations on one piece of data. And if we were to then go ahead and change this, let's go ahead and give it 2 pieces of data. Let's say that equates to a 1 and a 1. Well, now we're going to do 4 complete loops. Let me scroll up here. Pardon with me. We're going to do 4 loops through our neural network. We're going to say, hey, we're training. We have 2 pieces of data here. And so we're doing 2 iterations. So it's going to take these 2 values, put them in the inputs, run them through the neural network. Then it's going to take these 2 input values, input sets, run them through the neural network. That's training iteration 1. And then it's going to take all of them and run it through training iteration 2 again. And we're going to keep doing those iterations until we've either reached the desired error level or the desired count of iterations. When we're done here, I can console log. Once we have a trained network, I can console log. Let's stringify this because it's going to be JSON. We're going to JSON stringify net.toJSON. So I'm going to output the JSON of what I have here, and I'm going to stringify that so it's easy to see. So when our train network is done, this is actually what we've come up with. We have some sizes here. We can see our sizes are 232. You can change this in the options, but that's what it shows. And then here's our layers. Our final train network has biases and weights for all of our different layers. Biases and weights, you can see that we used a sigmoid activation function, which is the default. And then these were our training options and our default error threshold. There we go. We've trained a neural network, and this right here, this JSON object, is our trained neural network. We can now take 2 pieces of input without knowing the output, run it through this network, and the output should work. I say should because clearly this is just made up data and we only did 2 iterations. So that's how a neural network works. Hopefully you're comfortable now looking at a diagram like this and understanding what's actually going on, how it's calculating really complex outcomes from data that would be hard to predict otherwise. Neural networks are awesome. They're tons of fun. Get into them. The documentation for Brain.js is great. It's really easy to pick different activation functions, to change the amount of hidden layers in your network. Play around with it. Have fun with some data sets that are available online. And have a great day.